Better.
Okay, so we are.
Yeah.
So we're. Can everybody hear me, or does this help, or can you hear me better with this or without, or whatever? It doesn't matter. You're fine. Okay. Uh, we're going to go through chapter 2 tonight, and I'll explain to you the lab 2, uh, uh, and it's on under the hybrid text. So you go to hybridplc.org, and under that, then you go over on the left-hand side to hybrid text, and then chapter 2, and that lab 2.1 is in that chapter. So that would be where you would find it, and you would find all the things about it. Uh, this is a chapter on a beginnings of how you would understand where PLCs came from, and that's what we're talking about tonight. So basically, you may not think that this chapter has much value, but when I taught it previously, there was one student at least that came up to me and said, I'm going for an interview with a company in Cleveland, and they gave him he's electrical, but they gave him a test, and it was this problem 2.1. And he had taken that, he had done this problem, and he understood it, and they gave this problem to him. And this is a typical problem that you're going to get from an employer. You're not going to get a lot of sophisticated PLC ask things, but they're going to revert to something like this. And he was able to very quickly knock it out and give it to him, the answer, and show him how to do it. And they made him an offer on the spot for $82,000. And he was, anyway, I'm not saying that to brag about it, but this is kind of hitting on the area that an employer would like to see you have some knowledge of prior to all the things you can do with computers, because they want you to understand where they came from and all this kind of stuff. So that's kind of why we do this, but we also need it as a background and understand why certain things are the way they are. And I'm going to pass some things around. I'm going to pass some relays around to you tonight. And I will show the picture of it, what it is, and I'll pass it around. But basically, it gives you a little bit of a background, and also this lab uses one of these relays. So I want you to understand that one of the relays you're getting passed around tonight is the relay you actually use in your lab. So that is part of this, okay? And so the symbology of a electrical diagram, commonly called a schematic or an elementary diagram, uses symbology that is a little bit foreign to a lot of you. You've probably never seen these before, and there's a variety of ways that these symbols are pictured, but typically they're pictured in a way that gives you a little bit of an idea of what the device is. So if you were to look at it, you would say, oh, that looks like something that I've seen before, and in many cases, it kind of is. Some of them aren't, but some of them are. And these are from Visio. If you want to know where I picked up all my pictures, I'm a Visio. That's what all the things that my diagrams are from Visio. So if you want to know where did you get these pictures, these stick figures, and all that kind of stuff, Visio is what I did. And these are from Visio. Now you'll find different ones from different companies and different organizations, but this is Visio. And then these are the ones, the same thing, only they're the European version. European version goes up and down, American version goes left to right. That's about it. But they look the same, but they call them normally open, normally closed in the United States, NONC, and in Europe they call them make and break. So if you see a make or break, you're talking to somebody who's either from Britain or Germany or someplace in the EU. And if you're talking to, or maybe Canada, and if you're talking normally open, normally closed, you're talking to somebody in good US of A. Okay. Now, a ladder diagram that you would see in industry is a bus on the left, a bus on the right, vertical bus, and then the logic goes left to right. okay? Left to right. The coil, or the bit that is being set, is the last thing on the right. And this is the coil of a relay right here. And what does this look like? An O, right? Or zero? That's that. That's that device right there. That's why that's a circle. Looks like, maybe it doesn't look quite like a circle, but it kind of looks like a circle. That's why it's a circle. Now sometimes it's two parentheses, but you got the idea, right? And I want to pass this around and you can see it. Okay, so this would be a relay with this in it, and then this is another one, and another one. This is it taken, kind of halfway taken apart, and then this is the coil, and you can just start looking things over and pass them around. Just keep going back and forth and bring them around here, and this is the same thing. That's your coil. Okay, so here's what they sound like. All right, when they turn on, when they energize. Did not everybody hear that? Did everybody hear that or not? Kinda? Okay. So it's a mechanical device, right? It's a mechanical device. Anybody wants to come up afterwards and try this, you're welcome to. I'm not gonna pass this around because I don't want you to touch these two coil wires because they're hot. I don't want any accidents. By the way, everything in our lab is 24 volts. For a reason. You can't, I mean, you can't hurt yourself. You might be a little arc or spark, but you can't hurt yourself. This, you can hurt yourself a little bit. You can get killed with 12 volts if you're in exact ideal position, but I've been bitten up with 110. I don't like it, but you know, it's not good, but it's there. But anyway, you can come up afterwards. This is a little 12-volt relay, and in there is a regular relay, and then there's one that's taken apart, and you can see the insides of it. So this is a 12-volt relay, and this is the same relay with the guts exposed. Now the coil of this relay is the two pins on the one side. The contacts that come off of the relay are on the other side. And if you touch this is a 9-volt relay, it will work. It's not the best, but it will work. If you touch the coil pins to this, you'll actually get the contacts to change position. You'll actually see them changing position. So this one I can pass around, and you can actually see the contact switching inside. This is one that you can actually physically see. Now, why would we ever have 12-volt relays? Cars. Okay? Right? 12 volts in a car, right? So cars use 12-volt relays. Very cheap, because cars use a lot of relays. So you can pass that around and pass that on yourself. You're not going to hurt yourself. This is the kind of relay that I heard when I first walked into industry. These are the big boys, clunk really loud. Okay, this would be a regular relay. The big old style relays. The ones that are coming around before are a little smaller. These are NEMA, those are IEC brand, or this is the American style, that's the European style. They shrink everything down because they're more economical and they do everything smaller. But basically, you get the same bang for your buck you do with this, you do with that. It's a little bit more, beefy and that type of thing, but they do the same thing. Okay, this is normally open when there's on contacts, but they change contacts when you energize the coil. So at least you get a little bit of an idea what's going on. This is a motor starter. Does the same thing. Coil, closes. But this is contacts that are rated for a motor. Same exact thing, except for the contacts are a little beefier. Okay, same thing. What is a coil? an inductor, okay? I equals C dV over T, E or V equals L di over dt. You can't, when you open or close these contacts, they don't immediately shut down the current, right? So as you open and close the contacts, what happens? The current's got to go someplace. It cannot immediately go to zero, all right? Everybody? V equals L di over dt equal Eli. Voltage equals L, the derivative of I over derivative of T, all right? If I immediately goes to zero, what happens to voltage? What's the derivative of a step? Infinity. Nobody gets an infinite voltage. So you have to have a little bit of arcing and sparking because the current jumps across the contacts as it's opening. Okay? That's why they wear out. That's why coils and that's why you get so many on them, but you don't get an infinite number. Okay? And these are some smaller ones. I'm going to pass these around. I'm going to start these over on the other side so you can get a little bit of an idea of. All right, these are some smaller ones, and this is the one. This is the one like you're going to use in the lab. This is the exact one you're going to use in the lab. There's a whole bunch of these in the lab, so you can get an idea. Okay, so these are the ones. These are smaller ones. This is the same style, only we don't have anything. This is the smaller one as well. This is the old. This is 24 volt. Everybody get a chance tonight, right? Okay, so you go from left to right, usually. Now with electricity, does electricity care? No, it does not care. You can go up, down, left to right, right to left. With electricity, if you bring a circuit back around, you can do that. With a PLC, they had to compromise, and they only allow left or right. No right to left power passing at all on a screen with a PLC. So basically a PLC compromises that one aspect of an electrical circuit. You can't go right to left. See, I could take a circuit here and go back and feed back and then come back again. Does everybody follow that? Because I could draw anything I want and I can make that happen, and they do. But you can't do that with a program control. That's one of the compromises the PLCs did. Any questions so far? So that's called ladder diagram. This is a pictorial of a ladder diagram. This is a rung, a single rung of a ladder diagram. Okay, rung on a ladder. Now this is a push button, symbol for a push button, PB. Normally open. Now what is it about a push button? As long as you're pushing it, it is energized, right? As long as you're pushing it, you are actually pushing that down and making a contact there, right? That would be a normally open push button, NOPB, okay? There is a normally closed push button and a normally open push button, all right? There's your relay. Now, what about the names of these relays? CR, what does that mean? Control relay. Usually they use the word CR for control relay, but it could be anything. It could be X, it could be Y, it could be XYZ. It doesn't matter on a drawing what they call the name. In a PLC, the address or the name is extremely important. It's just like the name that you would assign a variable in a computer. You have to call it a specific name, and it has meaning, and it has value. In other words, you have to tie that to a bit or a word or something in the computer. But here, you can call it anything you want. CR is the typical name that is used because that designates something that we kind of think of as a control relay. CR, control relay. All right? Now, these relays have contacts on them. You see those and you hear them. When you hear that clicking, those are those contacts going open or closed. Okay? Now, this is a normally open contact. That's not a capacitor. As I said the other day, that's not a capacitor. That's a contact that when you energize, it closes. Everybody got that? This one is a normally open contact. This is a normally closed contact. This is the variable. This is the knot of the variable. If you look at that little line across there, that's kind of like the knot of that variable. So when you turn this on, it turns this on, which turns on this, which turns off this. Easy. Everybody got that? Okay, that's the course, by the way. If you get that, and no, I'm kidding you. That's just, but that is what the basis for that Lab 2.1 and most of the stuff. Okay, so there you go. The relay coil, which you saw and heard. The normally open contact off of it. The normally closed contact off of it. And this is what's going on inside. There's a spring, always a spring. There is a coil. So when you energize the coil, the steel core pushes against the spring and pulls the contacts down to the core. Okay, now this is just to show that change in that, and now this is to show that contact actually does energize. In other words, this not like a capacitor. There's electrical current that actually passes through that contact when it closes. And when this one, it opens. In other words, the switch opens. So we're really talking about Boolean logic. Here's some of the pictures of the things you're getting passed around. And here is I lost this, I don't have it anymore, but it's a DC contactor, but it has the same basic nomenclature as what you have, except for the contacts, they have what we call arc chutes, so that your arc does not jump out of that particular contactor, arc chutes. These are switches. Now, switches are different from push buttons. How? Once they are set, they don't change. You switch a switch to a position and it stays there. A push button, you let go and it comes back to a normally open state or a normally closed state, okay? Here is Eddie, former student, Ed, who is using a push button. Now, why would he ever do something like this? How many contacts are on that push button? I lost this. By the way, I had this for a long time and then somehow it got lost. Why would we ever have something like that? Because we need all those contacts for various pieces of logic, right? Is that correct? But now, why would we never design something like this? Each of those push buttons has a spring in it. By the time you add about 10 or 15 springs, can you push the button in? Physically, no. I mean, you can try, but it's almost impossible to do. Do you follow me? So there's no way you would ever put something like that out in the real world. You would have to do what? Go to a relay and then use the contacts off of the relay to do your logic. So you could do this, but literally your mind says this is not something you would ever do, and that's correct. Now in a PLC, how many contacts are you limited to? 100,000, 200,000, you get the point. It's like a bit that you declare in a program and then you can use it wherever you want it. You don't have to physically plan for it by wiring something, as opposed to here. What is this? This is a time delay. It's a physical, and I lost this one as well. This is one of the things that I don't think I have it anymore. But anyway, I have a timer on top of a relay, and you have two clicks. You have a click when you turn on the relay, and then you have another click when the timer times out. It's a pneumatic air bladder that actually bleeds air out. So you hear click, click, okay? So you have this bleeding of the air out, and then it does the second timer. Now, why would anybody use this? Where would this be used? When you need a delay of time, when something is a delay of time, you would use this. But how much does this cost? $100, $200, okay? It would have to be wired. If you look at a PLC timer, it's something that you can put in a time delay inside a program controller, and you get that time delay doing the same thing, and it's more accurate than this. And it also doesn't cost you a lot of money. And there's another bad side of this. There's an on-delay timer and there's an off-delay timer. And if you miss and you get the wrong one, you have to not only flip something, you can't just flip a flip switch on this thing, you have to physically take the one off and put another one on. It's very painful. So again, there's a lot of reasons for using programmable controllers over these devices. You still find these devices in industry, however, because for some reason or another, somebody has been afraid to take this off and put a PLC on. So they still use the same device as they used before. So anyway, everybody having fun passing those around? I mean, are they around? Is everybody getting them? Is everybody getting a chance? Okay, and is everybody getting to sign that thing? Okay, you don't have to sign it, just check your name. Okay, please do that. I mean, I need that back. I'd like the relays back too. Okay, so how about this? Now, do you ever see two relays in series? No, you do not. In the real world, why don't you see relays in series? Because relays have a voltage rating. And if you have a 12-volt bus, let's say you're using a 12-volt system, and you put two relays in series, each relay would take 6 volts. You would split it 50-50, okay? And the relay will not turn on with 6 volts. It might turn on with 9 or 10 volts, but not with 6. Everybody follow that? But in a PLC, they allow it. So you can't see this in the real world. You can see this in a PLC, because they'll let you put 10 of them in a row if you want to. Now, they mean the same thing. Why would you ever have two relays like that in a row, either series or parallel? Because they mean the same thing. If that thing turns on, if that machine turns on, or that thing turns on, whatever it is, it would be on with both of those bits. Why would you ever have two of them? Yes, sir? No, it's much simpler than that. You have two programmers. One wants to call it XYZ and one wants to call it ABC. So you have two different people, one that wants to call it something and somebody else calls it something else. And they both are right. You follow me? One is probably your controls person and one is probably your HMI person. And many times you get projects where you actually have two people working on the same control project at the same time. And I've had this where I was off programming and then I'd come back later in that day or the next day and I'd have another coil on there and I'd say, what is this? He'd say, well, I didn't like the name that you called it and I put my own name on it. And okay, you call it X, you call it tomato, I call it tomato. But that's how you do it. I mean, and it's a dumb reason, but it's the truth that you would actually do that. But it works, okay? So, you can do Boolean logic. Boolean. A and B. All right? You can do that. All right? You can do A or B. Right there's A or B. You can do the NAND, which is the not of A or the not of B. That's the NAND, not and. You can do the NOR, which is the not or, which is the NOR, which is the not of the or function, which is this one right here. You can do the exclusive or. You can do all these functions with relays. And you can do the not. Okay, you can do the not function. Now, these are the same symbols with the European, and I put them in there because, and I misspelled break, I spelled it braille, but this is break. We don't have any braille, we have a break contact. Okay, so this would be a make contact, normally open, a make contact, normally held closed, a break contact, held closed, a break contact, normally open. So that would be those four symbols. European symbols. That's the way they do. That's the way they describe them. Make and break. And that would be a symbology of a relay, or that's a pilot light, but that would be the symbology of that. Okay. And again, they did it vertically, or they did it horizontally. Sometimes they do it vertically. It's whatever. Now we get into. I do want to go beyond this just a little bit and explain the lab to you before I come back to this. But at this point in time, we take a break. If you're electrical, you can kind of, okay, for about an hour, you can take a break. If you're mechanical, you probably haven't seen some of this stuff. So we get you we take you through electronics. What's your digital course? 1100. Your digital course is 1100. Okay. For EET people, it's 2210. EET 2210. We take you through the fundamentals of these courses in about 1 hour. So you get what you need to know if you're mechanical in about an hour, or maybe an hour and a half. But we don't mess around here. We kind of, when I taught this course before, EECS, they just went right up. We just didn't stop here. We just kept on going. But when I taught this course to mechanicals, I got this. But we haven't had that stuff yet. When you talk about De Morgan, we haven't had what is De Morgan? And you probably say, I have never heard of that before. Well, after this little bit, you will know what the De Morgan is, and you'll know some other things. But it's a kind of a refresher. I didn't do the whole course. Obviously, you can't do the whole course in one night, but at least for a little bit, I'm going to go through that. But I want to go back to the lab next and go through that first. Okay, so here we go with, and we talk about motor starters in this area as well. I just don't have time to go through motor starters with you, but if you want to review this on your own, or you want to go back, I teach a course in motor control, and that's EET 4350, and I also have the material on the website for that, and we do touch on it in other areas as well, and we'll talk about it in chapter 10. When you try to find the short circuit current rating of a panel, I'll refer to that book as well. So this other course that I sometimes teach is useful, and there's some good information in it, and we'll tie that in when we get to that point. But this is something we're going to skip over for tonight. Okay, so again, this is lab 2.1, and I have this, the little 12-volt relay, and I used to use that 12-volt relay exclusively for this lab. You needed a breadboard, and I don't do it anymore. If you need a breadboard, if you want to do it 12 volts, you can. We still have these relays, but I would prefer you do it with the 24-volt relays and a screwdriver and wire, and I'll show you the rest of the components you need. Okay, so this is the one that I took that was just passed around that you can see the insides of. And there it is on a breadboard. And now we have the relay that we're going to use in this lab. And it is a 24-volt relay, and it has on it a diode. Now, why would we have that diode? If you get it backwards, it'll just turn off. It'll jumper out. Why would you have a diode on a relay? I already mentioned it tonight. You have a inductive kickback or feedback when you turn the circuit off. So when you turn the circuit off, that current's got to go somewhere. Where does it go? It chews up the contacts on a motor starter, but here it actually does that. The current goes backwards, and that's a flyback diode or whatever. But it's built in. You don't have to put it on. It's built in to that relay, so that when you turn the relay off, that current that's still in that inductor has a place to go, and it goes right around and back up and it dies, it decays with an exponential decay, and it's gone. But it has a place to go. Everybody follow that? That's why that's in there. And also, that is polarized. Terminal 14 is the plus side, terminal 13 is the minus side. And so if you hook it up 24 volts to 14, 0 volts to 13, you will succeed. If you hook it up backwards, it'll just turn off. So you have to hook it up polarized, okay? This is when you have to hook up polarized. Some of them that I passed around, the little one, the little 12 volt one, you do not have to worry about that. It'll work either way. But the 24 volt one is polarized, and you have to be careful. Now there are contacts on there as well, and they're 1 to 9 and 9 to 5, okay? And then there's 4 to 12 and 12 to 8. So if I want to use these, I can. In any kind of circuit that I want. They're not touching this coil. In other words, I don't have electrical contact between this and these, but when this turns on, this opens and this closes. All right? And here's the physical layout of those terminals on that socket of that relay. There's 14 and 13. There's your plus, there's your minus. And if you look really close, if you get your magnifying glass out, you can see those numbers on those terminals. They're there. They're hard for me to read, but you can probably read them, and you'll see those terminal numbers on that relay. If you've got the one that's the little 24 volt relay right now, you can probably look at it and you can see those numbers on it. Okay, and now this is a push button station, and the red is the stop. The yellow and the green have normally open contacts on them, but on the back side you can actually see a red or a green little tab, and the red tab is signifying a normally closed, and if that doesn't get you, if the red doesn't get you, the little NC gets you. I mean, NC means normally closed. All right? So if you push the button, does it open or close? It opens. If you let it go, it closes. So NC means normally closed. So it's normally in its reduced, in its relaxed state, it's closed. So if you want a contact that is a normally closed contact, I would use the red buttons. All right? If you want to use a normally open contact, I would use the yellow or the green buttons. Okay, because when you flip it over on the back, you'll see either this or this. Now, where are the contacts physically located? They're located between this terminal and this terminal. So if you want to have a contact, you wire into here and then you wire it from here, and the contact is in between the two. Okay? What is this side? I bet it's a light. Okay? That's a signal for a light. So you can ignore the light. Or you can, if you want to, you can wire it up. When the relay turns on, you can turn on the light. It's up to you. I don't care. But this is the side that you're going to use. Okay? That's the side you're going to use. Normally open, NO. Normally closed, NC. All right? I'll get this quite a few times. This is just it takes a while to get these terms down in your head. Normally open, normally closed. American terms, United States terms. Normally open, normally closed. Okay? European make and break. Make, normally open. Break is normally closed. Same. So you're saying the same thing, you're just saying it differently. Okay. Any questions so far? Now I'm going to give you a break on this. You can skip this part because this is the 12 volt relay, and I did it both ways, so you can do either one. But you can do this if you want. This is kind of a first circuit, and it shows you how to wire it up. And here's the second circuit. You can show you how you work it. Now this is an AND circuit. These are just testing to see if you can wire this thing up right. And here you would use a contact. Now I'm going to show you this in a second here, but anyway, I'm going to give you this. This is a AND of these two, and this would be a what? An OR of these two, okay? And this is a what? Ever seen anything like this before? Yeah, some of you have. This is what we commonly call in the United States a SEAL, S-E-A-L circuit. Okay, what does this do? Say again? It does what?
Seals on the energized bit to keep it up.
Yeah, it stays on until you hit the stop switch, right? So why would we use this? Okay, I want the fan on the roof to turn on this morning. When I walk in, I want the fan on the roof to turn on. So I hit the start switch. Do I want to hold my finger on that switch all day long? No. At night, I want to go home. I want to hit the stop switch and turn it off. Okay, and that's what it does. It stays on until you turn it off. Now, what else about this circuit is interesting? What if you turn off the power? Electric storm comes across. You have a power dip. Power comes back on. It is in the off position, right? Off position. So you have to restart it after a power dip. Why is that important? All right, I'm working in a factory. I am a programmer in a factory. All right, so today I finished the program for my machine and I walk out and I say it's working. It's working. All right, 3 a.m. get a call. That machine you programmed today or yesterday is not working. What's your first line of defense? Did you power off, power on? You might get 3 more hours of sleep if that happens, because it might be hung up on something. If you power off, power back on, you might get back to a good state. In other words, you might buy yourself 3 hours of sleep. If you didn't do that, if you did something else, you might have to go in immediately and fix the problem or whatever. But you might have gained 3 hours of sleep, okay? Did you power off, power on? Good question, always. And most of the time, oh, I forgot, and they go off, and sometimes they come back and call you again. But anyway, sometimes you get away with that. So again, it's a reset, right? If the power turns off, power turns back on, it's a reset of your functionality, and it might get you back to a normal position, and then they might be able to limp along until, by the way, the bad side of that is if it happened once, will it ever happen again? Oh, you betcha. You might have bought yourself a 3-hour nap, but you might have to that next day go in and find out why it did that, why it hung up wherever it hung up. If it hung up once, it'll hang up again. So what are we talking about in this course? We're talking about real-time computer programming. What we're actually getting down to is real-time computer programming, okay? Which is what kind of programming? Typically programs that you write, if you get it to work once, you are victorious. You succeeded. You're good. With this course and with this kind of thought process, if it can fail once, ever, it's bad. So basically you have to not only get it once to get it running, you have to make sure that you beat down all those extraneous things that can also go wrong in the process. Does everybody follow that? This is a much more rigorous, you have to beat down all kinds of stuff than not just the once through, done, yay, yeah. Not so in this course, and not so in real-time computer programming. If it can go bad, it will go bad, and if you ever see it going bad, you better go back and hunt for it because it'll go bad again, most likely. Okay, anyway, SEAL circuit. Now, I want to show you a little bit of how you can work at these and you can attack these, because they're not hard, they're very easy, but I do want to give you some heads up on this. Okay, so let's go back and let's look at this just for a minute. Okay, so over here, can everybody still see that okay? I showed you the normally open, normally closed positions of this guy, right? I did that. So terminal 1, normally close to terminal 9. Normally open to terminal 5. Okay, the same thing with 4. To 12. To 8. Okay. Now let's go down here, and this is 13 and 14, right? 14 is on the plus side, 13 is on the minus side. Now let's go down and look. Okay, so if I push my button, and I draw this with contacts on here, what do I actually say? So I come down here and I push my button, and I come to a terminal. If I put a terminal in there for the coil, what would that coil be? This would be plus 24 through the normally open of the button to terminal 14 to terminal 13 to 0 volts. That's exactly how you would wire it. Everybody follow that? Now here you have a couple choices. You can say, I'm going to be sneaky and I can use 9. So I can come down here and use 9. And then I can go to the normally open, which is terminal 5. To my light, to my normally open light. Did everybody follow that? So there's my light. And here's my other light. Whoops, this is the part that I can do that. And that's not, that there's no line there. And then I can go down here and use the normally closed to do 5 is normally open, 1 is normally closed. Terminal 1 is my other light. Everybody follow that? You see what I did? I can do it a number of other ways. I can use 12 and 8, and this would be CR1, CR1, CR1. 9, 5, and 1, I could use 12, 8, and 4, or I could do it the other way. I could say 9 to the 1 to 5, and then I could use 12 to 4 on the other side. I don't really care, but you got the idea, right? I can do it a number of different ways. There's a lot of different ways of doing this, but any of those work. Any questions about that? So now you've got a little bit of an idea about how to wire this. Same thing here. How do you do this one? Okay, how do you do this one? So here, you would go PB1. Everybody see that okay? Is that acceptable? To 14 to CR1 to 13 to 0 volts. This is 12 plus 24 and 0 volts. The second one is PB2. Same thing, 14 CR2 13. Now we go to war. So now we got to find a contact off of 1 and 2 that are both normally open. And how do you do that? Well, do I remember those, or do I have to go back and look? I probably have to go back and look. You find a normally open contact off of 9 to 5. So I can do 9 to 5 off of the first one, 9 to 5 off of the second one, and away I go. So basically I can do that. 9 to 5 gives me a normally open. So now I go 9, I put the 24 volts to 9 of CR1 to 5, and then 9 CR2 to 5, and that gives me my light. Or I could use the other one as well, okay? Now, I'm not going to do them all for you, but this one is the same kind of thing, all right? Any questions how that's done? Again, I would like you to do all of those. If you need to answer these boxes, for sure you need to answer those boxes. And this one, I definitely want you to wire and get it to work. Now, if you don't do this one down here, I'm not quite as concerned about, but I want to ask you, what's the difference between this one and this one? What is it about this one? It's the same circuit. It's the exact same circuit. But now I'm getting more sophisticated. I don't want to go up on the roof to turn on my fan. But if I have to service my fan, I want to have a button up on the roof to service my fan. So I have a push button station on the roof, and I have a push button station down by where I come in. And I can start it from either place. Okay? What is it about these? The stop is in series. The starts are in parallel. If you build this one, you build the first one, and just at least look at this one. If you have time, build this one as well. But you can start and stop that relay from either position. So that's what is about that one. Okay? Either place works. You can have a push button station with a start and a stop button in either at both places, and they both will work. Okay, any questions? So far, so good. Okay, now let's go back and look at.
Sorry, question.
Yes, sir. Yes, sir.
What's the lab that we need you to be there for, and it's the in-person?
I do not. I can't. There's just too many of you. All right. Do it at your as you can. And 2350 is the best place right now. I've been waiting a few days. I don't want to do this too many times, but every time somebody else rolls in and says, "Yeah, I want to be in your class," okay, I have to resubmit the names to get into 1100 and 2390. So I've been waiting a few days for that. You can get into 2350 now by keypad 4575 pound sign. You can get in there now. 4575 pound sign gets you into 2350. And those relays are sitting there, and those push button stations are sitting there. Now, how do you get 24 volts? Any of the programmable controllers has a power supply right by them with 24 volt power supplies. They're all 24 volt power supplies. They're all there. So don't tie to the 110. That's stay away. But the 24 volts that goes over to the PLC, you got a plus 24 and a 0. The red is the 24, the 0 is the 10, is the black wire. So you can do that. It will work with any color wire that you want, but we typically use red for the power and black for the neutral, although anyway, that's what we've typically done. And if you are missing a screwdriver, I told the tech to get some more screwdrivers. If you don't carry a screwdriver, that's okay. We have screwdrivers and wire strippers, but you need, if you can't find one, we are getting a bunch. We're getting a potload of them, but we always, what do we lose in this course? Screwdrivers and wire strippers, okay? It's just, it happens. So you would need a little bitty one. These are this is the type that you need, and there should be some around. If there aren't, I'll go find you some, but we're on track to get you a potload of these things sitting around in each of those rooms so that you can actually do these projects and you'll be fine. But anyway, if you don't spend any money in this course other than for anything else, you might invest in a $2 screwdriver that with a little bitty flathead on it. And you can look at this one. This is the type that I use. I carry it in my pocket because they're the ones that we use in this course. Little bitty flathead ones, and this is the sign. And I'm not telling you to go buy one. Probably be okay, but you follow me? They might come up short with this many people. No. How long it's going to take for us to work through the few screwdrivers we got left, and I told them to buy a bunch, and we may get them in this week, we may get them in next week, but when we get them in, and the wire, and we got wire, but the wire strippers and that, and you say, how many of these things do you have to do with this? One or two, and why would I ask you to wire it all? Just to see how long it takes to wire stuff. It takes a long time, and also, you may not appreciate electricians. You know, they're just the scum of the earth, right? No, they're not. They should be your friends. And after you've done a couple of these, you probably will say a little bit more kindly to them if you work with them. You know, I appreciate what you do, you know, they're maybe not your friend, but you have to work with them. You have to work with electricians, and you have to get them to do things with you. You just have to. You can't do it all. Now, you can come back in after they leave at 3:30 or 5 and sneak in and do stuff and all that kind of stuff. I know that. I've been there, done that all the time. You know, stay till 10 o'clock, do stuff after they've gone, and they come in and they say, what happened? I said, I don't know. But I'm telling you that you need to be appreciative of them. And, you know, after a while you get to know them and they get to know you. And anyway, so again, you need to appreciate that little side of it. It's not a big part of your work, but at least get just a little bit of wiring. Okay. Anyway, almost out of time. Did everything make it around? Yes, sir.
In terms of lab reports,
I want as small a report as you can get that makes it so that I can believe that you did what you did.
so we should have left.
No, I'm not going to do blackboard. I want a piece of paper that I can quickly look at, and there's like 70 students in this class. I cannot. I've got 4 courses. I got 4 courses. I teach the lab for this course. I teach the lab for the other course. For 3 courses, 3 of the 4 I teach the lab for. Now you do that and the math of that. And I also am managing the high school Rubik's Cube project. This is one of those, and why did I end up like this? Well, the other teacher that teaches with me, or that I teach with her, she went on sabbatical for a year, okay? And then the one guy that we were kind of encouraging to be full-time and all that kind of stuff, they didn't offer him full-time. And he finally just said, the heck with it, I can't do this with, you know, $3,000 or $4,000 per course, and I can't feed my family. So he basically left. He didn't totally leave, but he kind of half left. So I'm down to me, myself, and I, and this is one semester that I'm just, you know, putting blinders on and saying, I'm going to give you some tests that you should have some idea of what you're doing in order to pass. And in order to do that, you're going to have to go into the lab and do some work. Not a lot, but enough that you catch on to what's going on. I'm not going to make you fail this course because you're about ready to graduate. But on the other hand, in order to learn this stuff, you're going to, how do I do that? I trick you into going into the lab and doing some labs. That's why I give you 40 points for those labs. Okay, there's a massive number of labs here. Okay, there's a massive number of labs. And by the way, I will give, if you do the, and I'm going to write this into the syllabus, so it'll be on the web syllabus. It's not going to be on the one I handed out, but it'll be on your syllabus. 16 points for the white cross, 20 points for the total white on the top if you do the Rubik's project. Okay, so that gives you 20 out of the 40 points. So if you're planning on, if you already know what you're doing, but you want to do that, you can get good points out of that. 8 points for the safety one, 8 points for the Cognex one. And so what are these things he's pulled up out of, and I'll show you where they're at as we go through the course. So, and what is the Cognex? The vision system, the eyes, the brains of the eyes. That's the other side. There's 3 parts to automation for the most of the things that you do. The PLC, the vision system, and the robot, okay? And in this course, you're getting in spades the PLC. You're getting a little bit of vision, just a little bit, but not much. But you're getting the PLC side, real-time computer programming, a lot. You're not getting any robotics, okay? Say, why aren't we getting robotics in this course? Why can't we do it all? Well, I have, for the mechanical side, I teach the 4450 class in the fall, and I don't know if I'm going to do it next fall or not. I think I am, but I'm not really sure. We'll figure that out later. But in that course, I teach, okay, so you come into that course and you say, what am I going to learn here? Well, I'm going to teach you just a little robotics, just a little vision, just a little PLC, just enough to kick you into gear. And then you put it all together in the second half of the course and make something with them all together, tied together. That's the gist of that course. So that's a different animal, because in that one, it's the synergy of tying everything together. It's not the logic of processes like we do in this course. So we talk about, in this course, okay, you're walking into an issue or whatever, and how would I start programming it? How would I attack it? Not with a robot necessarily, but with everything else. How would I attack the logic for this type of a process? And that's what we're trying to do in this project, in this course. Here's a process. How would we start? How would we begin to look at how to control it? And what techniques would we use? Is it a sequential process? Is it a analog process? Is it a batching system? Is it a blah, 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 whatever? Is it a motion system? Is it a single axis motion system? That type of thing. What are we talking about, and how long would it take us to do it? And what are the pitfalls? And what about safety? What about if we have to make things safe? What do we do then? All those are critical things to analyze. And where do you start? And how do you prepare? And how do you look at things? And that's this course. This is a heavy-duty theory course. In a way, even though it's not theory, you just got hammered just a little bit with this one little thing about relays. And I hope that you can be able to take that and put it into a lab and then cement that in your head, because that's important. That little seal circuit is the basis for a lot of the things that we do. If you do it, you'll never forget it, okay? And you might get an $83,000 a year job, because that's what that guy said. He said, I went in and they only asked me the thing that you had already in lab 2.1, and he said, I did it and like that, and he said they hired me on the spot. Yeah. And I'm not saying you'll do that, but I'm saying I know where to hit a lot of the things, and this is one of them. And you're pleasing somebody when you do 2.1, because all of a sudden you can talk a lingo and a language that you couldn't talk before. You're talking about control relays. You're talking about normally open, normally closed contacts. You're talking about seal circuits, and you're talking about how to make them work and how to put those contacts together and how to wire that thing up. And all of a sudden they like you, because it takes you from the theoretical realm and moves it right into where that's what they do for a living, and they realize that it's something that you're willing to do. Now, I don't know whatever he did, or if he went there or whatever. I think he did. I don't know. But anyway, so let's go back and talk about what I was trying to do tonight, which is digital logic. Okay, so it's here in the hybrid, not the hybrid text, but the other brother, the EET 4550. Nope, not there. 44 MIME. MIME. Nope. Where is it? I can't believe it. I can't find it. It's here. I just saw it. I can't think where I'm at. Yeah, it's in MIME 4450. That was the one. I couldn't see it. Does everybody see this one down here called A Bit of Digital Logic under MIME 4450? Now, this is 3 chapters out of a book that I basically just took and cobbled together. Okay, so basically, we're going to have to stop tonight. We can't spend tonight starting in this because it's just too much. But I will expect you, we will go through this next Wednesday night, okay? So please, there's 3 chapters, chapter 2, 3, and 4, and if you're mechanical, you've never read through this stuff before, please just go through these 3 chapters, and the main things that are important to me are, how do you get a number from a bunch of bits? In other words, how do you get a Boolean number from bits? How do you convert a number from digital, from decimal to binary and back again? How do you do the conversion? And the other thing that I would like for you to learn is the De Morgan, how to do the negative of a function. So if you're looking at where this is going to go, I'll do it all in one night, probably, maybe 2, but maybe just one night. And it has to do with, I want you to be able to understand how you build, okay, is it 16 bits or is it a number? Yes, it's both, okay? And I want you to get that, because many times your program will work that way. It will be one or the other, or it can be both at the same time, 16 bits or a number. Sometimes it's 16 bits, sometimes it's a number. It can be flipping back and forth, and you can be doing both at the same time. It can be. So I want you to get that, 32-bit, how that's done and all that kind of thing, because we're dealing with, in PLCs, we're dealing with numbers a lot, and we're also dealing with Boolean logic. So, and the ability to flip back and forth between the two, and sometimes use 16 bits as a number, sometimes use it as a 16 control bits, is extremely important. And that's something that, if you haven't had Boolean logic at all, just read through these 3 chapters in 4450. It's called A Bit of Logic, and it's from the Floyd digital logic text that the EET students take, but it's the same book that is used for the EECS students. And chapter 2, 3, and 4 are the chapters that really sort of get you off of dead zero, and it shows you the gates, it shows you the pictures of the gates. And if you wonder where that's leading, the languages that you use in the PLC, there are 3 basic languages. One is ladder, but then one is called FBD, function block diagram, and function block diagram is these gates. So when you're studying the gates, the and, the or, the nor, the gate logic, you're actually building those on the screen. So that's called FBD, function block diagram. And you can flip back and forth. You can, for a while, you can be in ladder, then you can be in FBD, and you can be back in ladder, and you can just do all over the place. You can do that. And there's also a procedural language. It's a C-type language or a Python-type language. It's just a flowing, top to bottom, looping language that you can use as well. And you pick which one, and you can have them all three going at the same time. Okay? There are other languages as well, and we talk about them sporadically, but there's at least two other languages they use as well. So one of the goals is not for you to be so proficient in ladder that you forget about all these other languages, but to be able to pick which language is the best language for the application, and you work accordingly. Okay, so the gate language of chapter 3 of this is FBD, functional block diagram. So if you do not have any idea what these gates look like and how they tie together, after you've read chapter 3, you will have a much better idea. It's called functional block diagram in PLC lingo. Hopefully everybody gets home okay tonight, and I'll post this later on, and some of the people will get it signed. Now, did everything made it around? Did everybody get to sign this up? Did everybody sign this thing, or did they not sign it? Check off. If you didn't, come up and see me afterward. Did the relays all get around? Are they up there in front someplace, or they're there? You take care. We'll see you. Rest of your week. Have a good Sunday. Take off. Okay.